Greetings, this is Sean, and today I'm going to be talking about Ohm's Law, and that is what a lot of you have been asking about with regards to resistors and how to figure out how much voltage and whether or not you've got too much power and that type of thing. So this is what we're going to be talking about today. And I created this little PowerPoint type. It's actually a keynote on my Mac, but it's basically a PowerPoint presentation. Anyway, Ohm's Law is basically the process of calculating resistance, current, voltage, and power in an electronic circuit. And so that's what we're going to be talking about here. And we got a few terms here to define. Voltage is the potential energy in a circuit, and it's measured in volts. Current is the measurement of the flow of volts through a current, and it's measured in amps, and it's also represented by the letter I, which I can't remember why is I, but it's represented by the letter I. Resistance, which is the force against voltage to limit the current in a circuit, and it's measured in ohms. And power, which is the measurement of the usable output being created by the current through resistance. And I'll explain that a little bit more when we get into it. And it's measured by the letter P or W, W for watts. And then the capacity, which I'll just touch on briefly, it's the amount of usable energy in a battery. And you only see it in a battery, and I'll show you a few examples here in a little bit. And it's measured in milliamp hours. And anyway, so those are the terms that we're going to be using today. And just to give you an analogy, think of the electronic circuit as a water hose that's attached to a barrel. And there's a little video that I'll play here in a minute. And the little box that you see, we'll pretend that it's a barrel that's full of water, and that hose is attached to it. That's actually just a hose reel. But anyway, we'll just pretend it's a battery for the purposes of this video. The spigot on the barrel is the switch. The hose is the wire. The water that's running through the hose is the voltage. The speed of the water going through the hose is the current. And if you put a kink in the hose, or if you have a little nozzle or something like that, that would be like the resistor. And the spray coming out of the end of the hose is like our LED, and that represents the power of the circuit. And as you can see here, when the water's flowing, there's a nice current, but when I kink the hose up, the current or the flow slows down. And the less resistance, the more flow or the more current. And the more I kink it or the more resistance, the less flow or the less current that comes through the hose. So that's an idea, just to give you an idea of what we're looking at as far as how things are related to each other. And another way to relate it to each other is with these two, what they're called Ohm's Law pyramids. And the one on the left is voltage, which is the V, I is the current, and R is the resistance. And on the right-hand side, the P represents power, and the I is current, and the V is voltage. And the way that you calculate these, you put your hand or your finger over the letter that you're trying to find. So if you're trying to find voltage, for example, you would put your hand over the V, and you would have what's left is current times resistance. So if you're trying to find out the voltage that you want, you multiply the known current and the known resistance to get the voltage. And if you want to find out the current, you put your finger over the I, and you divide voltage by resistance. So that's what's left over. And if you need to find resistance, then you take the voltage and divide it by current, just like that. Same on the other side, except you've got P for power. So if you're trying to find power and current and voltage, it's the same way like that. And then there's another calculation which kind of comes into play, where if you want to find power but you don't know what the current is, and I kind of broke it down in steps there. P equals, on the right hand side, P equals I times V. And since you don't know what the current is, you can take the voltage and divide it by resistance, which gives you the power equals the voltage squared, or voltage times voltage divided by resistance. These are I'll come back to that here in a little bit. I'll explain a little bit better. This is a copy of the data sheets for an LED, and when you design a circuit, you need to know a lot about the circuit that you're trying to design. And so for LEDs, the most important thing, well, there's several important things, but one of them is the forward voltage, which is highlighted there in yellow. And this typical, the 1.85, that's on average what it takes to make the LED light up. And the 2.5 volts next to it, that is the maximum amount that it'll take before the LED gets burned out. That's one way to think of it. Here, on the bottom part of it, you have two that are important. Actually, there's three that's important. I forgot to mark one of them. The reverse voltage, the 5 volts, that's the maximum amount of voltage that the LED can handle if it's put in backwards. And the peak forward current above it, the 155 milliamps, that's the most amount of current that you can put through an LED before it would burn out. And the one above that, which is the DC forward current, is 30 milliamps. That is the amount of current that it draws to make it turn on. And the one above it, the 75 milliwatts, that's the power dissipation. That's how much power it takes to make it turn on. So those are the ones that are important for us in our discussion today. So now I'm going to give you an example using the Tinkercad. This is an online app. It's at tinkercad.com, and you just need to sign up. It's free, and I'll have a link to it below. What I've done was I created a circuit here. I've got several circuits on this page, but this one here is where we're going to start. And this power supply here is going to represent like a USB power supply, like if you were plugging it into your USB charger for your phone, for example. And this resistor here is our power limiting resistor, and I've got a bypass for it here with this switch. And then I've got 3 LEDs in parallel, which we talked about before. And I've got these 2 switches here will turn off the yellow and the blue LEDs. And instead of using red here for the positive, I use the blue wire for the blue LED, and the yellow wire for the yellow LED, and the red wires for the red LED. This is the main power switch. Like our discussion earlier, this is like the spigot. This is the water tank. The wires are the hoses. The current that flows through it is the water, and the spray from the end of the hose is the LEDs. This meter, this is a voltmeter. It will measure the amount of voltage that's at this point here across this LED, at the same time this one and this one. So it'll give a complete total how much voltage is being used in the circuit by these 3 LEDs. And this one here measures the voltage across this resistor here. So I'm going to start the simulation and show you how this works. See, I've got 5 volts, which is what your USB phone charger runs on. And I need to flip this so that this resistor will be in play. And right now, all 3 LEDs should come on when I turn this switch on, which it does. You can see all 3 have lit up. And right now, it's drawing 1.92 volts of power. Now, the voltages on here are not the same as on the data sheet, but they're really, really close. Everything has to be accounted for. As you can see, 5 volts is coming out. There's 3 volts being dropped across this resistor. There's 3 volts basically going through this resistor. And there's 1.92 going through all 3 of these LEDs. And right now it shows that it's drawing 14 milliamps of current. So what I can do is I can take this 3.08 volts that's going across this resistor, and let me pull up my calculator. You take 3.08 and divide it by, remember it's voltage divided by resistance equals current, divided by this here, which is 220 ohms. So we divide by 220 ohms, and that equals 0.014, or if we multiply it by 1,000, which is what milli stands for, is 14 milliamps, just like it shows down here. So if you remember our, and it's dropping 1.92 volts across these three LEDs as well. Now what I can do is I can turn off these, and you'll see that more voltage is going through this LED, but not very much. When I turn off one of them, it goes from 1.92 to 1.95, so only 3 or 30 milliamps or millivolts is going through, is being added to each one of these as we're going through them. And you'll also notice here now, if I were to turn off this resistor here, you'll see that they all have too much voltage, or current. See, the current through the LED is 483 milliamps, and the absolute maximum is 20 milliamps. And so you got too much current going through there, and that's why it blows up. Same with this one, same with that one. And even if I turn these off, you'll see that all that current is still going through that one, and all of the voltage. Remember, 5 volts was too much. It was only able to handle I think it was 2.2 milliamp or millivolt or volts or something like that. I can't remember what it was. So that's for the purpose of this resistor being in this circuit, is to limit that amount of current that's going through these LEDs. Excuse me. So, and you can also change this resistor, which right now, like I say, it's a 220 ohm resistor. If we made it, say, a 1000 ohm resistor or a 1 kilo ohm resistor, you'll see that the voltage here goes down, the voltage across this goes up, which means that the current, see, now it's 3.17 milliamps. So less current is going through, and that's why these get dimmer. So what we try to do is figure out what is a good resistance that will give us the amount of current that's, not too much for the LEDs, and so that they don't get too high. Now, if I remember right, it was 20 milliamps. So if we want 20 milliamps to be here, we're trying to find the current. We need to take the voltage, which we know is 3 volts. Actually, we need to take 5 volts, and divide it by this resistor. Well, we don't know what the resistor is, so we have to take voltage divided by current, and that'll give us the resistance. So if we take this 3 volts here, let me go back to my calculator, take 5 volts, which is what we're applying, and divide it by 20 milliamps. Oops, wait. 0.02 equals a 250 ohm resistor. So, oops, if I put a 250 ohm resistor there, well, I got to do it by this voltage here. Come back, calculator, come back. We take this 3.1, we'll just round it up, and divide it by the current, which we want it to be 20 milliamps. 0.02 equals a 155 ohm resistor. So if we make this a 155 ohm resistor, you'll see it's almost 20 milliamps. And that's how we figure. Now, I don't know why this is different, but anyway.
Actually, the reason why that's different is because through a circuit, current remains constant. As you can see down here at the on the power supply, it's 19.7 milliamps, and we don't know what the resistance is across the LEDs. And those LEDs do have some resistance, and that's what causes them to light up. So without knowing what the resistance actually is, I mean, we could take a voltmeter and actually measure the resistance across it, but instead what we can do is use the Ohm's law pyramid and take the voltage that we know that's across it, which is almost 2 volts, and divide it by the current, and that would give us the resistance across that. So current remains the same throughout the circuit. So you would take the total resistance, which is the resistance of that resistor and the resistance of the LEDs together would give the total amount of current. Since it's 5 volts and 19.7 milliamps, we know that, you know, the resistance, you know, that's how we would have to, you know, calculate the resistance across those LEDs. So if we take, say, we'll just round it up for just to make it easier. We'll take the 2 volts across the LEDs and divide it by the 20 milliamps that's in the circuit. And so 2 divided by 0.02 will give us a resistance of 100 ohms. So basically there's a 100 ohm resistor where the 3 LEDs are, and that's the difference. That's why I had such confusion, because there wasn't a resistor there, and I just wasn't thinking at the time that I originally recorded this. So hopefully that will all make sense. Anyway, on to the presentation.
So that's how we determine how much current we need for the circuit, and what the voltage to use and the resistance to use. Now let me show you a different circuit here that I did. This one here is very similar, except what I did was I put, no, not this one. Yeah, that one. Oh, it's so hard to do. Command plus. This one here is basically the same circuit, except instead of having 1 resistor, I've got 3 resistors here. So the current, it goes from here through this main power switch, or the spigot, and then it divides off and it goes up to this one with its own, each one has its own resistor. And when I turn this on, you can see that they're all dropping 2 volts. And this 40 milliamps is for all 3 of them. So you take this 40 milliamps and divide it by the 3 for each one. So if I were to turn this one off and this one off, you'd see it's only drawing 13 milliamps across this one LED. So that's another way, but I find it just easier to use just 1 resistor, and you know, for the circuit, instead of having to have 1 resistor for each LED. So now with power, let me go back to the other circuit. Let me turn this one off. We'll go back to this one here. For power, if we have, since we've got these 3 that are all on, we have 1.94 volts, and remember, power is current times voltage. So if we take the 1.94 and multiply it by this current, 19.7, that equals 38 watts of power is what is being drawn on this circuit.
Actually, it should be, I should have multiplied the 1.94 times 0.0197. It's milliamps, and I did it by 19 amps. So the actual calculation should be 0.038218, which is 38 milliamps, or milliwatts is what it actually should be. I goofed. Oops.
Okay. Now, this resistor here, we would take to find the power that's going through this, because that's important too. We take this 3 volts here and multiply it by the current. So we take 3.06. Now let's say we didn't know what the current was. We only know what that resistor is. And remember, resistance is voltage divided by current. So you take that 3.06 and you multiply itself, or square it, and then divide by the resistance, which is 150 ohms. And that means that resistor is pulling that much power, or 0.06 watts or 6 milliwatts of power is going through that resistor. Okay. So, and that's important too, because you have different sizes of resistors that you can get. You can get 1 watt, half watt, quarter watt, and so that's where you have to kind of make sure that the I always go with half watt or 1 watt resistors anyway, because that, you know, usually that's sufficient enough. So anyway, that is basically how you determine current through a voltage or through a circuit, and how to determine what size resistors you need for how much current you need or how much power you need. Now, if we just as an example from a previous discussion we had, this one here, these LEDs are in series, which means that if one goes out, they all go out. But I've got them right now bypassed to where I can have just 1 on or 2 on or 3 on by having these wired the way they're wired. And I've got 5 volts just like before. So if I turn this on, you'll see that each one of these is dropping 1.67 volts, and nothing's going across this resistor right now. But it's only drawing 38 microamps. That little odd U is called is the micro. There's a sign for micro. And so, and you can see that they're barely on. If I were to turn these other 2 off, you can see that it's drawing so much current or so much voltage that it's way too much. And you can see that it's pulling 79.8 milliamps through that one LED, and that's why we don't wire them this way in series, because one, they're going to be really dim, or you only get 1 or 2 that are about ready to burst with that much voltage. And now I can limit that by putting this resistor in place, and that will help to limit the amount of current that's going through these. But at the same time, it's still very low voltage, because each one of these has to draw its own power for each one. They're not sharing the power. They have to take their own. So that's why there's so much voltage being dropped across each one and so little across that resistor. I can still turn those off and it'll work for the one. So anyway, that is what I wanted to show you here. So
the last thing to talk about is the capacity of a battery. Now, if you notice down here at the bottom, it says 2450 milliamp hours. What that means is if you were to have a device or something attached to this battery that drew 2,455 milliamps of power, it would only run for 1 hour. That's what that means. So if you've got a circuit like we've been working here, it's only using 20 milliamps. You take the 20 milliamps and divide it into the 2,450, and that's how many hours you'd be able to run that circuit on this battery for 1.2 volts. Of course, to get the 5 volts that we would need, you'd need 3 of these batteries. So you take the 2,450 milliamp hours, and well, you would still it would still be the same amount of time, because all the batteries are being drained at the same rate. You don't drain one and then drain another and then drain another. But if you had the 4.5 or the 5 volts coming off of these 3 batteries, excuse me, you would have enough voltage to be able to make that work properly. So anyway, but if you had 3 batteries that was only using 1.2 volts, then you would multiply the 2,450 times 3, since you're only using 1.2 volts, and you'd be able to run it for 8,000 hours basically. But anyway, that's what the capacity of a battery is. So you take the amount of current that's being drawn from the circuit and you divide it into the amount of milliamp hours for a battery, and that's how many hours you'd be able to run that circuit on that one battery. So anyway, I just thought I'd throw that in and share that with you. As far as what the capacity of a battery is, that 2450 milliamp hours is the one that's important. So anyway, hope this has been informative. If you are confused, please don't hesitate to leave a comment below or email me, and I'll be glad to explain it to you better. If you want, I'll be glad to do a live stream, and we can discuss this live, and you can ask questions there or send me some questions, and I'll be glad to answer them in a live stream for you. I don't have a problem with doing that. I don't know, some of you may have noticed that I started up a live stream a couple earlier this week or late last week, whatever. I can't remember when it was. I was just testing out my software, and I forgot to set it to private instead of public. So that's why you saw what you saw, if you did happen to see it at all. So anyway, let me know if this was helpful. If it's not helpful, let me know that too. I want to be as helpful as I can and help you to understand how electricity works. And anyway, that's all for this one. I know it was rather long, and I apologize for that. Anyway, have a better day, as I always say.